Section 1, and now we're moving on to a brief outline of graphs shown in your book in Section 2. Now, I've started there with what I hope most students would have understood from school. The basic line graph is shown by y equals mx plus c. X and y are two variables, m is the gradient, and c is a constant found at the y-intercept. Now, a well-known graph, there's a little bit of a spelling mistake there, but we'll get rid of that, is the temperature scale Fahrenheit and Celsius. Okay, now let's just go back to the general formula. Now, most people will read the textbooks and you will find y equals mx plus c as the general line for the general equation, I beg your pardon, for the straight line. Okay, now what does this mean? Right, y and x are the two variables. We have two variables. They vary with each other. As one changes, the other will change. M is called the slope or gradient. And some of you will remember probably from school days that it's found by, it's the rise over the run. This is a term that some students use. Okay, rise over run. How much it rises by how much it runs. In other words, there's your right angle. So how far it goes up in terms of how far it goes along. So if this is, say, 4, this is 2, then the gradient m would be 4 over 2. Rise 4, run 2. It runs for 2, but it rises 4. Okay, so that would equal 2. Now, c is a constant for this particular equation, and it's where the graph intercepts the y-axis. So we call it the y-intercept. Okay, now if I give you, or the lecturer gives you something simple like this, y equals 2x, then straight away you know it's a straight line graph. M straight away equals 2. I wonder if you know what c equals. Doesn't look as though there is a c. There isn't, because c equals 0. So if I asked you to sketch this, this is how you would write it out, or draw it out very quickly. Okay? Now this is positive y, 0, negative y. Okay? This here is positive x, and along here is, again through 0, is negative x. So you quickly sketch the axes. Where will this run? Well, y equals 2x. There's no y-intercept, so one point is definitely there. So when x is nothing, y is nothing. And this will run through in a straight line. So that if I were to look at numbers, if that was 1, this would be 2. If that was 2, this would be 4. If that was 3, that would be 6. Because I'm taking the x value, placing it in here, and getting the corresponding y value. So if your lecturer requires you to do a table of values, okay, which often are done prior to the construction, but here we can do it very quickly, then this is how we do it. Okay, when that's 0, that's 0. I put that 0 into the formula, 2 noughts are nothing. Okay, when I put 1 in there, 1, 2 ones are 2. I put 2 in there, 2 2s are 4, and 3, 6, etc. Okay, so this is very simple. Now, to work out why the gradient is 2, we know it's 2. Let's just check this. Watch this. This is 1, that's gone up to 2. 2, that's gone up to 4. 3, that's gone up to 6. So, if I make a right-angled triangle here, then looking at this previous idea of rise over run, as I run 3 units on the x-axis, I rise 6. So I say, okay, m equals rise over run. This is the gradient. I've gone along 3 units, but I've risen 6 equals 2. And that, in fact, fits with what I was given. Now, that is all really basic sorts of information. All right? Let's have a look at something that is not in the booklet, but we can do it here. Supposing the lecturer says, right, we're going to look at this graph. Y equals 3x minus 2. Okay, now again you can do your table of values, or if you're reasonably good with maths you can work this out as follows. Put in your x's. Okay, here's your plus y, 0. This is the basic sort of format. Now 3x minus 2, straight away when you look at that you see the two variables are x and y as before, but this gives you extra information. M you see is 3 and c is negative 2. So I think, oh right, so here we go. If I go down to negative 2, then the graph is going to go through there. It's going to intercept at that point. So when x is nothing here, y is down here. This is fairly steep, okay? So when x is 1, if I go up to 1 there, and I put it in here, 3 1s are 3, minus 2, this is 1. So it would be up to that point there. If I go to 2, 2 3s are 6, minus 2, this goes up to 4, 2, 3, 4, we're up here somewhere. So you can see, it's in fact it's quite steep. It's going to go down something like this, all right, rather steep. So that's the graph of y equals 3x minus 2 cutting through here. If I draw a little triangle, if I just take this section here, there's a right angle. Now, how far have I gone here? Well, 1 to 2, I've only gone a run of 1. Here, this is 4 minus 1, this is 3. So m equals, as we had before, rise over run, which is 3 over 1, which is 3. And that corresponds to the gradient there. Okay, so with practice you'll be able to do a lot of these sketches. Straight line graphs are usually very easy, they're quite straightforward, without having to do a table of values unless the lecturer requires it for extra marks. So you need to think about that. Okay, now if we have a look at the next little feature in the booklet there, well-known graphs include curves. So here's a classic one of y equals x squared. The values go shooting up because they're getting bigger very quickly. And on the other page here, I've drawn in some graphs that you will maybe come across depending on what course you're doing. Y equals e to the x, exponential curves, again shooting up. Y equals log, there's a log graph there, here, and y equals x is your straight line graph. All right. Now, not in the booklet, but what I'm going to show you now is something that's rather interesting, and we'll bring in some logarithms as well in a few minutes. Have a look at this. If you were a biological engineer, now think about that, you would be interested in population studies. Okay, and all these biological engineers do a lot of this work. If I give you this equation, P equals e to the t, where P is the size of a population and T is the time taken for organisms to grow, then we find something rather interesting happening. This is P and this is time, say in hours, for example. We can do it in whatever unit we like. Okay, now population numbers go up like this. When t is nothing, we know that e to the naught, anything to the naught, is 1. Remember the earlier studies that we've done, okay, that anything to the power. So in other words, the population here goes through 1. As t gets bigger, this gets bigger very quickly. Let me show you. We'll bring this in. Here's a calculator. Now, shift on the log gives us the e function. When it's naught, 1 is the value. So e to the naught is 1. The calculator confirms that. All right? And we know from our log theory that that in fact is true. Do it again. Supposing it goes to 10, e to the power 10. Wow! 22,000. So after 10 hours, say here, this has shot up to, say, 22,000, all right? Which is typical of lots of populations. They could be bacteria populations, they could be fish, they could be any sort of organism that breeds rather rapidly. Let's have a look at this one. Let's do e to the 20. Oh, and there we go. We're going off the scale. It's absolutely humongous. So this thing is going to race off like that. And this is why it's important in population studies. Now, what happens if we go backwards? Where does this go? Well, log E, let's go backwards. Now, can we put in a minus? We can. Watch this. Let's put in -5. What do we get? Very small, 0.007. All right, it's coming down here. So -5 is way down here. And as we keep going, this keeps going off to infinity. So log E, quite interesting. Oops, I've got the wrong one there. We need log E. There we go. Now, let's go to -10. Oops, let me just do this again. Log E, there we are. Now, -10, I'll put that in, close it off for good practice. And you're getting more zeros. So it'll go to infinity. It never actually touches the x-axis, so it goes racing off. So that's a good one for population studies, if you were, for example, an engineer in biological systems. All right, that's what they use. And this is a typical population studies growth curve. Okay, we're not going to be dealing with that quite so much, but the idea gives us some useful insight into the next topic that I want to show you, which is quite interesting. Watch this. Now, if you are dealing with thermodynamics, if you're a thermal engineer, for example, you will be dealing with thermodynamics. Let's just put that in. Then a topical problem is, in fact, at some stage, you'll come across the very famous cooling curve problem. Now, what does that mean? All right, well, a cooling curve, we're interested in looking at materials heated up to a terrific temperature. How long will they cool? So this can be temperature in degrees Celsius. There's 0. Off we go again, and here's time. For example, we'll just use it in minutes. Okay, if I just bring that in so you can see. There we go. Now, instead of the curve going up this way, we use this curve. We say, all right, let the temperature equal e to the negative t. Aha. So there again, when t is nothing, and we've got this one, this still equals 0. In other words, -0, e to the 0 is still 1. So it's still going to go through this 1 point. But what will happen is, when t is negative, a negative and a negative is a positive. So it'll come racing down from a very high value. And here we go. This is the bit that we're interested in. It goes racing off there, and it never reaches. It goes off to infinity. Okay? This is a typical cooling curve, and this is the behavior that we can study. That's the point 0, 1 from here. All right? So we heat up a metal, okay, and it cools down over time. We know that it does because if this was 1 minute, this would be e to the -1. If this was 2 minutes, it would be e to the -2, e to the -6. So it's dropping down. All right? The negative function there, the negative power, means that it's actually dropping down. So that's the sort of thing that we're after. Now, how does this affect you? Well, engineers often have to do problems like this. Experiments are done and equations are formed from actual real data. So we have something like this. T degrees C equals 10 degrees, for example, plus 90 multiplied by e to the -0.4 t. Your two variables here, you've got T temperature and T little t, which is time. Now, this value here is normally chosen as room temperature or a comfortable temperature to be handling the material. So, what we can say from this is as follows. What is T, big T, when we first start, when little t equals nothing? Okay, can we work that out? Well, yes, we can. We want to find this, so we say, right, big T equals the 10 plus the 90 multiplied by e to the -0.4 multiplied by 0, because t is 0. This is the start of the actual cooling. Nothing times this power is nothing, so effectively this is again e to the 0, which, as you remember, is 1. So now we've got 10 plus 90 times 1 is 90. So we have 100 degrees Celsius as our starting temperature. Okay, so that's nice and straightforward. We know we're starting at 100, so here we go. Write this in again, T equals 10 plus 90 e to the minus 0.4t. Okay, often the question is, how long will it take when we want to find t? All right, so the examiner or the lecturer might say find t when the temperature is, say, 20 degrees. See, that's a reasonable, comfortable temperature to handle. So now you've got to solve the problem, okay, putting all this in. So let's see if we can do that. Typical problem using all this information, your log information, knowledge about the graph behavior, blah, blah, blah. Here we go. So we substitute the value. So 20 equals 10 plus 90 e to the minus 0.4t. Now, step 1, we can get rid of this. So 20 minus 10 equals 10, okay, which is 90 e to the negative 0.4t. Now, what we have now is 10 equals 90 e to the negative 0.4t. This multiplies this. I want this term by itself, so if I take this to the other side, I've got 10 over 90. I do the opposite process, remember, change side, you change sign of the operation. So now we're in a very strong position to work this out. This is as simple as it can get before we bring in our famous taking logs of both sides. Again, you don't have to write it down unless you want to impress the examiner. If you think there are more marks going, put it in. Okay, so this is what we do. I notice that I'm using E. It's an exponential, it's a growth curve. In this case, it's a decay curve or a cooling curve. So I will use natural log. So here we go. We can say, right, natural log of 10 over 90. Okay, and you can simplify that to 1 over 9 if you wish. Equals, now remember, this power comes down. Okay, this is going to be negative 0.4 t multiplied by natural log E. Okay, now you think, oh, hang on, that's right. We've got natural log here, so we're in the right ballpark. This comes down. I want this, but you'll say, hang on, this simplifies even more because you'll realize that this is equal to 1. That's why this works. So now we have natural log 10 over 90 equals negative 0.4 t times 1, which is just itself. Okay, so to get t, I simply rewrite this 10 over 90. All right, divide that by negative 0.4, and that gives me t. So if I now invoke the calculator, let's see if we can work this out. Hopefully we will. Natural log, and I'll put 1 divided by 9. Close it off. That's the same as 10 over 90. When I said you can cancel, 10 over 90 is the same as 1 over 9. Just saves you doing a little bit. Okay? So that's that little bit. Now, if I divide that by minus 0.4, hopefully, there we are. We've got the time. And we used it in minutes, so therefore, t is 5.49 minutes. And that would be more than adequate to get you the full marks. Your examiner or the lecturer might say to 2 decimal places or just to 1 decimal place. So there we see the whole situation. We've got a cooling curve, okay? So this is a cooling curve or a decay curve. Sometimes it's called a decay curve, right? Or in your case, it's a cooling curve. And we see that it does have an equation that shows its behavior. We can plot this out, and here's a typical equation that's often, these equations are derived from practical experimental situations. So the engineers will know what equations apply to the type of material that they're using. So we need to know, in this case, how long it takes to cool down, say, to 20 degrees. Any temperature can be used, but the point I'm making here is that the 10 degrees here is probably the room temperature. It doesn't get any lower than that. unless the room temperature changes and we put a new value in there. But this is how it works out. A few steps, taking logs of both sides, doesn't matter. I chose natural log here because this cancels out, all right, and simplifies the working. Let's turn this around a bit. Okay, we've got a little relationship here in electrotechnology, and we've been given some values by the examiner or the lecturer, and he's requiring us, let's have a look at this, he's required us to find little v, given that big V is 100, and t, the time in seconds, is 6 seconds, RC, which is your, I think, a time constant from memory, that's given us 2. So can we find little v from this? So here we go, we write out the solution, and usually a good idea as you're thinking about this is to write down what you have been given. Okay, so start with this. Now the next stage is to substitute your values in. So then this becomes little v equals, now this is 100, so we put that in, 1 minus e, which is a constant, it's in your calculator there, minus, now t is 6, and RC is 2. Close the brackets. Okay, simplifying this, v equals 100, bracket, 1 minus, now this is e to the negative, is 3. Okay, so what we now have, we can work this out, this is going to be 100 times 1 is 100, minus 100 e to the negative 3. Okay, and that's what little v gives us. Now we can bring in the calculator. Let's see if we can work out what this little bit is here. Okay, so it's 100 e to the negative 3. So 100 multiplied by, now shift log, e up. Okay, if you look at the calculator here, this is 100 times e raised to the power. Again, the Casio will open up the bracket. You have to put in the relevant term, which is minus 3, and close it off for good practice. So that will give you 4.9787. Okay, so that's what that is. So what we now have is that v equals 100 minus this term, which is 4.97. Okay, so we can call it, say, 98. We'll round it off to 2 decimal places, and that will give you, if you can put that in, that's going to be actually 95.02 or 95.1 if you like, okay, which is volts. So let me just show you that again. You can in fact do this whole step here in one line. This is the beauty about the calculator. Let's see how we go. So 100 times 1 is just 100, minus 100 multiplied by shift e up, open bracket, minus 3, close bracket off, equals, there we go, 95.02. Okay, so from the calculator point of view, the exact answer is 95.02. I've just used 2 decimal places, but that should give you full marks, and your examiner should be quite happy with that.